Hey, this is Mr. Ward, and I'm doing a video on number 26 from the 2018 Math MCAS for 8th grade. And this is a transformation question, number 26. And there's another transformation question I'll probably incorporate into this same video. So 26 and another question. So Trevor's been drawing stuff. He drew this L on a coordinate plane, and then he's going to rotate it 180 degrees clockwise. All right, first thing to note, 180 degrees clockwise will be the exact same thing as 180 degrees counterclockwise. So we could pretty much ignore the clockwise, but sure, we'll do that. So we're going to be rotating 180 degrees, and so this L is going to be ending up around here somewhere in this quadrant. Okay, now there's a way to figure out exactly what it's going to be, but it's basically going to look like this when we rotate it 180 degrees. So, and that would work if we rotated this way as well. So find the one that matches it. So first of all, you can rule B out and you can rule D out because they are not in the opposite quadrant. 180 degrees means it's going to be the exact opposite from the origin. And if it's a rotation, then it's going to be twisted like this. So it's not going to be in this, and it's not going to be, so it's going to be twisted relative to its original position. All right, so A is the one that we want. I just want to take a moment on C because C could be a distractor. C is, instead of a rotation, C is a translation, which means it's been slid and it keeps its same orientation. So it's been slid down and to the right a certain number of units. So C is a translation and not a rotation. All right, so I want to note the four basic types of transformations. There's translations, which is just a slide left or right, up or down, or a combination to make a diagonal, but it keeps its same orientation. So it would still read like an L, right side up, if it was a translation. Then there's rotations, which we've just done. You can rotate 90 degrees, 180 degrees, go clockwise, counterclockwise. You can do other amounts of degrees, but that will require some trigonometry that you don't have yet, but it's doable. So that is a rotation, but it keeps the exact same shape, just changes its orientation. It has a rotational orientation. Then there's reflections, which are mirror images across a line of some sort. Oftentimes that's the X or Y axis, but it could be other lines. MCAS, I believe, will stick to just the X and Y axis. All of those maintain the original shape. They may change the orientation of it, but they maintain the original shape in its exact same size and angle. So it will be congruent. We call those rigid transformations. Rigid transformations, translations, rotations, and reflections are all going to lead to congruent shapes. A dilation, on the other hand, can lead to a similar shape. A dilation is an expansion, so scaling up or scaling down of a shape while maintaining all of its same angles and proportional side relationships. So a dilation is called a non-rigid transformation, and as long as it is dilated by a factor other than 1, it will be a similar shape instead of a congruent shape. All right, I'm going to pause this. I'm going to go to one. I think there's just one other transformation. Okay, I think there's actually two. So number 31, triangle JKL is shown on this coordinate plane, and we're saying it's going to be translated 2 units up and 5 to the right. So we're asked about where K will be after this translation. So this is K right here, and we're going up 2 and 5 to the right. So that means we're going to go up to this level. We're going to go up to this level here, and then we're going to go to the right 5. So we're going over to the right to here. So this will be our position. Now, you can use the graph up to and over 5, and you'll find our point, which is at 2, 1. We can find 2, 1 in here, and that's the answer. The other way you could do it is this. We can just identify our point K, our original point, which is at -3, comma, -1. And since we are vertically changing by 2, we can add 2 to the y value, and we're horizontally going 5 to the right, which means plus 5 to the horizontal component. And then we can add that up, and we end up -3 plus 5 is 2, and -1 plus 2 is 1, and that is our point. So that's the other way you could approach that. All right, I'm going to pause and go to the next one. By the way, this is a rigid translation because it's a translation, rigid transformations, translations, rotations, and reflections. It maintained all of its measures, so it is congruent. All right, so this one is related to transformations because we're talking about which triangle is congruent to Laura's triangle. The one that's congruent, that is going to be the one that has all the same side lengths. If it has all 3 side lengths, it will have all the same measures. This is a congruency test called side, side, side. You'll learn more about it in geometry, but if all the 3 sides of of 2 triangles match up and are the same measure, all their angles will be the same too, so they will be congruent. So you're looking for a triangle that has 5, 5, and 8. All right, 5, 5, and 9 is a fail. 7, 7, and 10 is a fail. 10, 10, and 16 is a fail. 5, 5, and 8 is the one we want. Okay, I'm going to note that D is similar but not congruent because all the sides are 2 times what they were in Laura's triangle. So 2 times 8, 2 times 5, 2 times 5. So that all the angles will be the same, but it won't be congruent. It will be similar. And these two, nope, not even similar. So they're not similar or congruent. And this one is not congruent. It's just similar. So our answer is B.